Okay, I think it's recording. So this tutorial, I feel like I don't have very strong intuitions or understanding about the stuff that's in this tutorial. But having said that, it's none of it's that difficult either. So, um, but I will probably need your help to get through it, just with some of this stuff of manually calculating deviances and stuff like that. So. Um, We set the stars off again, set a seed, load the car library. Oh yeah, no worries. Okay. Okay. Okay, so we're looking at MROS again. And yeah, I guess we're still predicting labor force participation from all these other variables. So what's the sample size? 753. We now fit the generalized linear model. The logit link is the default. So yeah, we've seen all this stuff before. That's a logistic regression. That's a summary. Gives us back our coefficients, which, as you guys remember, these are predicted changes in the log of the odds of participating in the workforce for a 1 unit increase of these predictors. Null deviance, residual deviance. I think this is Aikaki information criteria. Have we talked about that? Has Frederick talked about that? Okay. Okay. So now we compare two models, and we've seen this as well. And this is the type 2 ANOVAs for all the different predictors. Okay. So our first job is to calculate the residual deviance for the full model, similar to R-squared error. And note that the log likelihood of the saturated model is equal to 0. He says, in my solution, I use the data yes variable, a for loop to add the contribution of each entry, and an if statement to look at yes versus no. So, according to Frederick, you guys talked about this on Wednesday. So, what is the mathematical formula for calculating residual deviance by hand? Yeah, so say that again. Log of M1 log of saturated. 2 times. Yeah. So 2 times log of the first model. And what's the first model? I kind of thought it was saturated model minus.
If you just want 2, then that would be saturated. They're both negative. So easier would be yeah. So 2 times the log likelihood of saturated minus the log likelihood of the model.
Okay. And here he's told us, note that the log likelihood of the saturated model is equal to 0. So we can just change that to 0, right? Okay, so, but how do we get this thing? How do we get the log likelihood of the model? Did you talk about that on Wednesday? So this is our formula for getting the residual deviance, but we still need to figure out how to get the log likelihood of our model. Did you discuss that Wednesday.
It's just the it's like the y hat value for every.
Y hats, yeah.
And then we would do the negative log of that y hat value.
Okay.
But it's for each observation.
Okay.
We
So,
did it like a table.
So sum of the negative log, did you say?
Well, I guess we're not doing anything, so we don't need to be negative.
Hmm.
But we have, basically, your likelihood for the model would be each observation of y hat log.
Okay. Yeah, I think that's more or less it. The formula that Frederick has used, and this is where my intuition breaks down a little bit, is he's basically said it's we sort of separate cases into whether they were a yes or a no. And if they were a yes, we basically log y hat. If they were a yes, and we take the sum of all that. Yeah, exactly. And then we take the sum of the log of 1 minus y hat. And this underscore I just means that we do it for all of them. If no. And then we add those two together. And that's log m. So how would we actually do that in our well, first off, we need some way of separating if cases were yeses or nos, right? So how do we work that out? We did.
And then,
Okay.
but I feel like that's like too complicated.
So we did if else and then it was 901 that it's correct and
Well, that was when we wanted to know if our prediction was correct or not. We used if else. But there was actually a simpler way just to classify them as yeses or nos. Well, okay, so here's what just an easy way of doing it. So we can create a logical operator just by saying, what's our data set called? MROS. Okay. I'll probably use the data from the model. Model LFP. So this is just I'm asking a logical question of is this variable equal to yes? And it gives me back trues or falses. And so data yes just becomes a vector of trues and falses that matches up with our data set. And can, yeah, I guess like technically you don't really need this step, but it potentially it makes things a bit clearer. So let's say now using this, I want to get this sum, just the sum of the logs of the y hat i's. And we're doing it on the full Moroz's model. So I guess it's just Moroz's mod, right? Yeah, that works. Okay, so how would I get those y hats for a start? Moroz.mod. What next?
predictions? I don't know. Would you have to go into the model?
No. The model should store our fitted values. If we just go $ fitted values, we've got the predictions that our model made. And you can see these are in terms of probability, they're all between 0 and 1. Okay. So then I guess, yeah, we need to only select those of them that where the data was equal to yes. So how do we do that? Index by data, yes, exactly. So this, now instead of getting the full set of them, we're just taking those that where the data was yes. How do we take their logs? Just log, and then put that inside the log. And how do we take the sum of it? Sum. Very intuitive. Okay. So let's call this sum yes and save it. And sum yes is negative 217.4807. And it's, yeah, like I think it's not intuitive, and it's weird that you start getting these negative values and then you turn them back into positive values for the deviance and stuff like that. And it's all just because we're taking logs here. And logs of numbers between 0 and 1 are negative. So that's why like adding all these together gives us a negative, yeah. Okay, but now we need the opposite. So now we need sum no. So it's going to be similar, but what do we need to do now? Exactly, yeah. So I'll just cut and paste this. And if we index by minus data yes, that's going to reverse. Well, or will it? Let me actually. No, it doesn't. Exclamation mark, exactly. Which just adds not data yes. So the trues and falses become falses and trues. And we don't just want the fitted values, we want what? Yep, 1 minus the fitted values. So hopefully everybody sees what's going on here. Everything inside this guy is what's going on here. We're just taking the sum of the logs of 1 minus our y hats, if no. Okay, so that's sum yes, sum no, and then that means that our residual deviance is going to be what? It's 2 times 0 minus, and then I guess it's just these added together. Sum yes plus sum no. And that looks right. Summary mraz.mod. Yeah, 905.27, and then what we calculated was 905.27. So yeah, that's how you do it by hand. I was just playing around with this, trying to develop more intuition for it, and I figured, I just figured out that, okay, so say our data is a yes, and we made a really good prediction, right? Then we would be logging, so say our prediction was 0.99 for this case, and this case happened to be a yes. Then that case would only contribute tiny bit to this sum, right? But say we made a very bad prediction for this case. Or say like we still predicted 0.99, but this case happened to be a 0, not a 1. Then 1 minus 0.99, if we log that, we add a lot more in the negative direction to this sum. So we get a larger negative for making that worse prediction. If we had a predicted 0.01 for this case, and it happened to be a 0, that means our prediction was pretty good. So the addition to this sum would be smaller, right? And, this goes on forever. Like, say we had predicted all these zeros and ones. So we predicted there's no chance this person is going to be a yes, and it turned out, like we predicted, that they were not going to be a yes. We add virtually nothing to this sum. But if we had made that prediction and they had been a yes, we would be adding a lot more. So it's just, it's measuring for each case how far away our prediction was from their true value, which are just zeros and ones. Okay. Exercise 2. Now calculate the null deviance. So the null deviance is the deviance obtained from the mean response, similar to SS total. Compare the values to those obtained in the summary. Okay, so what is the mean response in this data set? And how do we calculate it? Yeah, so how do I do it? Well, yeah, but that's going to assume that like those yeses and nos, it knows which ones we are interpreting as ones and which ones we're interpreting as zeros. So we can, well, we can actually just take the mean of data yes. Yeah, because it always thinks of trues as ones and falses as zeros. So we can actually just say mean data yes. And that tells us that in our sample, the mean response of all those zeros and ones was 0.57, basically. Okay, so in the null model, this is just our prediction. This is our y hat for everyone, right? So you can probably tell me we basically just need to do what we did here, but use this guy as our y hat. So if I copy and paste this, and I am going to say just add like null to these guys, so I'm not losing. I might just call it null div. What do I need to change here? Sum of log of m response. Although that's only going to do it once, and we need to. Actually, I'm curious if we still use data yes, if that's going to make it, because we don't just want to add one log of this mean response, right? We want to add however many as we had yeses. So I'm curious if it's going to, no, that didn't work. So, no, because then we're going to multiply by something and then take a log. So I guess what we want to do is find a way to just repeat this in a vector however many times we had yeses. So
the first table and then you're trying to calculate a different mean for each time, or there's one mean?
It just needs the mean as many times as there are data points.
yeah, so for all our yes cases, we're treating the mean as the y hat. But we can do it this way. So say what you said again.
So we just do this and then at the end multiply by the yes.
Okay. I think that's going to work.
And then you sum that. So First we
Well,
take the log, then we multiply.
multiplying it will give us the sum if we multiply it by the number of yeses. So,
No, but the product will be a vector with
mm,
zeros and sometimes means.
all right.
Right? If the output
We-
will be
Yeah.
vector
We're
zero,
thinking
zero,
of
mean, zero, zero, mean, mean, mean.
we're thinking of this in slightly different ways. So tell me like exactly what to do.
So multiply that log
Mm-hmm.
rest multiply by data yes,
Multiplied by theta. Yes. Interesting.
and then we sum those.
Nice. Actually, yeah. That works. Does everybody see what's happened here? So we, instead of assigning for all our yes cases this probability value and logging all those probabilities and taking the sum, we're logging it once and then multiplying it by data yes, which sort of interprets that as this single value multiplied by a certain amount of ones and a certain amount of zeros, which is kind of achieves what we want. So I can put that there. That was smart. Okay, so now what should go here?
Multiply by exclamation number yes.
We should, and we should do one extra thing too.
Do we subtract here?
Yeah, because it's our y hat. The mean mresp is our y hat, and here we have to log 1 minus our y hat because if we predict something very high but the case was a 0, it's actually a very bad prediction, right? So the true value was 0 on the.
First take the log 1 minus m rest and then we multiply that by
Yeah,
the inverse.
exactly. So yeah, this is convoluted, I guess, at this point, but this should work. Let me just see. And then I need to change this to null. And that gives us for the null div 1029.746, which I think is right. 1029.75. Cool. So exercise 3 says calculate the change in deviance of a full model with and without age. Yeah.
So with that, some no. So previously it's 1 minus the likelihood times data no, sort of, right? But in the second function, it's 1 minus the likelihood, and you take the log of it, and then times.
Mhm.
So why it's two different operations?
Well, it's actually doing the same thing. So here we take 1 minus the fitted value for all the no's, and we log them,
Right.
and we sum them, right?
Yeah.
So here we've just sort of, here we want to do the same thing. So we want to take 1 minus the fitted value, and then log them all, and then sum them all for all the no's. But logging 1 minus this sort of mean response in the null model just gives us one of them. It doesn't give us as many as we want. So that's the reason we just do this. We calculate what this value is once and then multiply it by data no to get how many we need. So then we can take the sum of all of them. Yeah, and it's not really, yeah, it's treating data yes as a vector of ones and zeros, right? So it's like when we just look at what's inside this bracket, we get like an entire vector, a bunch of zeros where we've multiplied that value one minus the p by 0, and a vector of, or just a bunch of negative 0.84s where we've multiplied that value by 1. So then we have to take the sum as an extra step. But if we actually just worked out, well, how many no's are there, we wouldn't have to take a sum. We could just multiply this by that number. It would get us to the same place. So it's doing the same thing, just in a slightly different way. Okay. Now calculate the change in deviance of a full model with and without age. Obtain a p-value from the chi-square distribution. Perform the type 2 test to check your result. You can do this both with the ANOVA and the ANOVA function. Do it both ways so that you understand it well. Okay, great. So, yeah, now we want to figure out a change in deviance from the full model or from the model without age to the full model. So what do we need to calculate first before we can calculate that change in deviance? Sorry? The new model. Well, we've run the new model. That was mros.mod.2. What's that?
We need to get one without age.
I think, yeah, that was mros.mod2. Oh no, we didn't. Compare it to mros. No, that took out K5 and K16. Yeah, you're right. We need to run a model without age. So let's use this. And how should I, Yep. And what else?
So we need to also remove kids under. Wait, no, that's not kids.
Yeah, K5 is kids under 5. K6 to 18 is kids from 6 to 18.
So is it age of a person or kids?
I think it's age of the person.
So we put kids back and then we just do minus age because
Yeah.
What's the dot dot?
Yeah, so dependent variable, regress the dependent variable on the independent variables minus age. Yeah. It's just like a placeholder for same onto same minus age. Like, yeah. Cool. I think that should work. Great. Let's have a look. Summary. mros.mod.3. Okay. So, okay, walk me through it. How can I get the, oh, what's my next step? Get the deviance? Yeah, but we want to do it by hand, right?
So we need to calculate the change in deviance.
Yeah.
We calculate-
Okay, fine. Let's just.
I'm fine.
All right, but how do I get it from the model then? If you guys are so smart.
I don't know.
I mean, this is a
CSI and ask him.
this is
Yeah.
this is this is a common thing that you have a strong suspicion that something is in there in a model, and you just need to pull it out, right? So something you can do is just $sign and just see what's available for you, deviance. But we need to make sure we're getting the right one. The residual deviance we want is this 930. So this gives us 930. Okay, so that's going to be our res div 2 shortcuts. Great. All right, so change in deviance will be what?
The residue
Yeah, although which one's going to be smaller?
residue
Resdiv 2. So, well,
T.
resdiv will be smaller, right? So which one, if we want the change? Yeah. Yeah, so I named it resdiv 2. Probably it's a bit of a misleading name because that's the sort of smaller model that's nested inside the other one. Okay. Yeah. Yeah, exactly. Right. So, what have we been calling this value? The change in G, exactly. G. Okay. And our G is 25.59814. And I doubt anybody here knows how to get the p-value for that. Because G supposedly is chi-square distributed. So we need to sort of ask R to tell us what's the p of 25.59 according to a chi-square distribution. I think it might be p chi squared. All right, let's see how this function works. We give it a q. I'm going to guess that's our G. We give it a degrees of freedom. We tell it a lower tail. Log p equals false. Non-centrality parameter? That's interesting. Let's leave that alone. I think it's just going to be p chi squared of G. What would our degrees of freedom be here? And should we be looking at a lower tail or an upper tail to get our p-value? Sorry? Upper tail. Yeah. Because if you think about a distribution and we have this positive value, probably we're interested in the proportion of that distribution higher than our positive value. So lower tail equals false. And that gives us back 4.20445 negative 7. I think that's right. Let's just check ANOVA. mros.mod.3 is the smaller model. mros.mod is the larger model. Deviant 25.59, that looks familiar. Hasn't given me a p-value, but these deviances look very familiar. This degrees of freedom looks very familiar. So I'm going to say that this is all in order. We can also do big A ANOVA on the full model, which is basically, as you guys remember, it's asking for the same thing. It's asking compare this full model to the smaller model just minus each of these predictors. And for age, there's that change in deviance, there's that p-value. Yeah. So that all worked, well done. Okay, so comparing deviance to sum of squared errors. This is interesting because all the code is kind of here for us, but we just need to answer this this question. And the question is, well, first off, we run a model predicting prestige, and it's the same model, but we ask for the summary of it in two different ways. We ask for summary prestige of mod.lm, then we ask for summary prestige of mod.glm. So even though we've run just this normal ordinary least squares model, when we ask for the GLM summary, it gives us back residual deviance and null deviance. So this just shows you that even the ordinary linear model fits into this generalized linear model framework. And the question that we have for you guys is the residual deviance given by R unitless, or does it have units? So compare the deviance in the GLM model to the sum of squared errors in the LM model. So the deviance that it gave us was 5053.6. Yeah. So it's basically asking us, like, try to interpret this residual deviance in the output, in the GLM output from this OLS model. So this is just a normal linear model that we're running. But we're fitting it with GLM, right? So this is continuous predictor and continuous outcome, continuous predictors. But we're fitting it in the GLM format. And we've also fitted in the LM format. And we're just trying to make sense of, well, what is this residual deviance? What is this deviance of this model when we do it this way? So we want to compare the deviance in the GLM to the sum of squared errors in the LM model. So we know that we can get the deviance of the GLM model. It's right here, 5053.6. But we want to compare that to the sum of squared errors from the LM model. So how do we do that? How do we get the sum of squared errors from the LM model? It's not in that output, right? At least I don't think so. No, we get F statistic, R squared, blah, 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 but we don't get sum of squared errors. So how do we calculate some? Yep, or there's an even easier way. Residuals, right? So we can just go sum of our LM model, residuals squared. And we see, wow, it's the same. So deviance is just like sum of squared errors. And then there's this question: is the residual deviance given by R unitless, or does it have units? Who has sort of a feeling for what that question means? Like, how do you interpret that question? Sort of. So if something was unitless, what would that mean? Not exactly. Yeah, it's kind of being normalized onto some kind of scale. So if something did have units, what would that mean? Yeah, not exactly. So it's kind of just asking, like, this sum of squared errors and this deviance that R gives us, does that have sort of an interpretation related to the scale of our outcome variable, right? So if we took our outcome variable and multiplied all scores on it by 1,000, say, would this change? Right? So if something was unitless, that would sort of mean that it wouldn't change. It's been sort of like making something a z-score. It doesn't matter what the original scale is, right? It's not going to change your z-score. But if something has units, then it does depend on that original scale. It does have an interpretation related to the units of that original scale. So that's what we're trying to ask. So
It's like it would, right? Because if we have the mean that's in the silver units, and then we calculate deviation from that mean, it retains the units, and then we just square and add them, so units are not normalized at any point.
Yeah, exactly, right? And if our entire scale had have been like a scale from 1 to 4 instead of a scale from, say, 1 to 10 or a scale from 1 to 20, that's going to affect our sum of squared errors, right? Because with a larger scale, we get bigger errors. And so we get bigger squared errors and we get a bigger sum of squared errors. So, I mean, the easiest way to sort of demonstrate would be maybe to say, okay, what's our data set called? Prestige. Let's say prestige, prestige ds for different scale, and I'm going to just say well, let's just make it into z-scores, for example, which is something people often do with variables. And I might just say z-score, prestige z-score, and so I'm just converting my units to a different scale, and then I can just see that if I run the same model, change it to GLMZ, and I change the outcome variable to prestige z-score, I get a different residual deviance. So this is all this question's asking, is like, does the deviance that R gives us have an interpretation in terms of, like, is it related to the scale of that variable? And it is. And that's what sort of Frederick got to at the end, is he was basically saying in SPSS, it's not like that. It gives you something called a scaled deviance. R gives you an unscaled deviance. This bit at the bottom, I'm going to let you guys go through on your own. I didn't really know the point of it. I kind of went through looking at it. But yeah, there's no other questions that you have to answer. And so I will conclude this video. I guess I'll put it on YouTube if anybody needs it. And yeah, pretty easy tutorial, I think, in the end. But yeah, just stuff that is a bit, yeah, not super intuitive, not that easy, I think, to get your head around. Okay.